Hi again. Based on the forces during a driving cycle, we will calculate the traction power, and by integrating that power, we will determine how much energy is required for traction and braking during the driving cycle. This is useful when analyzing how energy demanding a particular driving cycle is, and it can also be used for a rough estimate of how much energy can be saved by recuperative braking in that cycle. The same way of calculating energy will also later be useful when we analyze energy flows and losses in different parts of the powertrain. To determine the energy, we first calculate the traction power. The traction power equals the traction force multiplied with the vehicle speed. This product is calculated for each time step in the driving cycle, and the result is a vector of traction power values during the cycle. This is a plot of the traction power during the end of the NEDC cycle. The variation of traction power during a driving cycle has similarities with how the traction force varies. However, since power is force times speed, the power varies much more with speed than what the traction force does. Therefore, the highest power in this cycle is at the high speed, even though the force in this cycle have its highest values at low speed. The traction energy is the time integral of the traction power. If we calculate this integral for the whole NEDC cycle, the result is 3,530,000 joules or watt-seconds. Often it's preferred to measure energies in vehicles in kilowatt-hour. We can convert energy in joules by dividing with 3,600 seconds per hour to get the result in watt-hours. That result is then divided with 1,000 to get the result in kilowatt-hour. For the analyzed vehicle driving the NEDC cycle, the traction energy required is 0.98 kilowatt-hour for a 10.9 kilometer drive. Note that this is the mechanical traction energy measured at the wheels of the vehicle and not the energy used by the powertrain. That energy will be higher due to losses in the powertrain. There is a problem with using this total traction energy as a measure of how energy demanding a driving cycle is. The problem is that positive and negative powers will be handled differently by the powertrain. Therefore, we should rather calculate one energy when the traction power is positive, illustrated by the orange area in the diagram, and another energy when it's negative, illustrated by the red area. Note that the positive energy is the energy when the powertrain is in traction mode, and the negative is when the powertrain is in braking mode. In coasting mode, the traction power is always zero, and therefore there is no energy used in that mode. In this diagram, we can see that the energy in traction mode is much bigger than the energy in braking mode. That is seen since the orange area is much larger than the red area. Where does this negative energy come from? As can be seen in the diagram, it is only during deceleration we have negative power in this cycle. This is because the energy comes from kinetic energy, which have been stored in the vehicle during accelerations and which is returned when the vehicle decelerates. There is one other possible source of negative traction energy, and that is downhill gradients, in which potential energy, which was stored when driving up a gradient, is returned when the vehicle is driving down again. The NEDC cycle does not include any gradient, so that type of negative energy cannot be seen in this diagram. We can now calculate the energy separately for traction mode and braking mode. The power in traction mode can be calculated as the maximum of the traction power and zero. When the positive power is integrated for the analyzed vehicle in the NEDC, we get 1.34 kilowatt-hour. In the same way, the power in braking mode can be calculated as the minimum of the traction power and zero. The energy in braking mode for this vehicle is minus 0.36 kilowatt-hours. Based on the energy in traction mode and braking mode, it is possible to determine roughly how energy consuming a driving cycle is. First, we analyze a powertrain which cannot recuperate any brake energy, like a conventional combustion engine powertrain. The required energy in traction mode is 1.34 kilowatt-hour. No energy is recuperated, so the net energy required for traction is 1.34 kilowatt-hours. All the 0.36 kilowatt-hours energy in braking mode will in this case become losses in the brakes. Now we instead assume that the powertrain has ideal recuperation, which can take all the energy in braking mode and store it without any losses. This stored energy can later in the driving cycle be used to propel the vehicle. The traction mode still requires 1.34 kilowatt-hour, but of that 0.36 kilowatt-hour can be taken from the stored recuperated energy, and then the net energy required for the driving cycle is only 0.98 kilowatt-hours. So, with a powertrain capable of complete and lossless recuperation, the 1.34 kilowatt-hour required to drive the NEDC cycle is reduced down to 0.98 kilowatt-hours, a reduction by 27%. The 0.98 kilowatt-hour net energy consumption is the theoretical limit for how low the net traction energy can be for this vehicle in the NEDC cycle. However, a real powertrain cannot recuperate all the energy. It has some losses. Most of the losses are in the electric machine, power electronics, and battery. There are losses when the braking energy is converted from mechanical energy into electric energy and stored in the battery, and then additional losses when that energy is later converted back to mechanical energy. Some of the braking energy may also be lost if the brake needs to be used in a few situations with high braking power. A rather good powertrain can recuperate about 2/3 of the braking energy. For such a system, the energy in traction mode of course still remain 1.34 kilowatt-hour, but this time only 2/3 of the 0.36 kilowatt-hour is recuperated, equal to 0.24. That leads to a net energy for propelling the vehicle of 1.1 kilowatt-hour, which is an 18% reduction compared to a powertrain with no recuperation. The remaining 0.12 kilowatt-hours are losses. Note that the relative size of the energy in braking mode compared to the energy in traction mode tell us how valuable a powertrain with recuperation is in the investigated driving cycle. In city driving, there is typically a lot of braking energy, and then a powertrain which can recuperate saves a large percentage of the energy. A city bus is probably one of the road vehicles which can recuperate the largest percentage of the traction energy, due to its very frequent acceleration and decelerations. When driving on a highway with only small gradients at relatively constant speed, a powertrain with recuperation will save only a small percentage of the energy, since the energy in braking mode will be very small compared to the energy in traction mode. This lecture has shown how the traction power is calculated from the traction force and vehicle speed. The energy in traction mode is calculated by integrating the positive traction power over the driving cycle. The energy in braking mode is instead the integral of the negative traction power over the driving cycle. The two energies can be used to estimate if a driving cycle is very energy consuming or not, and how big potential to reduce the energy consumption a system which can recuperate energy has. Thank you for watching.